So you'll see that it's kind of like wrong, but it's not wrong. So first one, what does a pH of 7 most likely indicate about the water quality? Most of you should know, no, I won't say most, all of you should know that a pH of 7 is neutral. That's where we like our water to be. So if you're looking at an indicator of water quality just by the pH, then we would say it's safe to drink because it's 7. If a pond is located in an area with significant amounts of air pollution, which health measure would be most directly affected? So what would happen if you're near a place that has a lot of air pollution like Los Angeles or New York? And air pollution is carbon dioxide. When it reacts with water, it makes an acid. In our notes, we have that pH comes from air pollution mostly. So if you have a lot of air pollution, you have acid rain. We talked about acid rain. And acid rain gets into our waterways, it lowers the pH. Which would lead to the greatest reduction of dissolved oxygen in a lake? I've told y'all before that dissolved oxygen is a big indicator of water quality. There's probably be several questions on your test and your benchmark about it. When you have a reduction of dissolved oxygen, it could most likely be from increased nutrients, so those nitrates and phosphates, which causes algae blooms. And those algae blooms take over the water source, whether it's a lake, a pond, whatever, and there goes your dissolved oxygen. Which would most likely happen to biological indicator species if there is a sudden increase in pollution? In our notes, biological indicator species are those macroinvertebrates, and in the notes it says they're sensitive to pollution. So if they are sensitive to pollution, that means that not only would there be a decrease in the population, so there would be less of them, but the ones that are there would not be of good quality. They'd be sickly looking or small or just not right. So significant decrease in population, less of them, and then they're poor quality. If you see that happen, then you know your water's probably no good. All right, what will happen if there's a fertilizer leak into a freshwater lake? Most of you put that it's bad, which is true. So what I was looking for, though, is that something along the lines of, like this one, there'd be a large amount of nitrates. That's true. Algae blooms. I was looking for algae blooms. Or extreme rapid increased growth of plants. Something along those lines. What if there's an increase of air pollution? This is the same question that was asked above. A lot of you, I think only a couple of you put pH, with something would happen with the pH. So the pH would go down, which means the water become more acidic. So that's the answer I was looking for. The water would become more acidic, the pH would drop, something along those lines. Does it have really anything to do with dissolved oxygen? Y'all got any questions about those? No? Okay. All right, we are moving on to oceans. You're going to hear a lot of terminology that is similar to what you heard in the freshwater, but we're going to apply it to a larger source of water, and the ocean is really unique. It has a lot of properties that are very, very helpful. It affects a lot of things, including our climate. But we're going to start with just the question that I think I get asked the most is, why is the ocean salty? Where does the salt come from? So we're going to be talking about ocean water composition. So get out your notes. I'm on page 58. Whatever your next blank page is, turn to it, please. And we're going to go through ocean pretty quickly. I still have one more activity I want to do with those water bottles y'all have been collecting for me. But it'll have to wait till next week because there's stuff I need to go along with it that's going to have to wait till payday. So I'm shooting for maybe Monday. And then we're going to get through oceans by next Friday because you have a test on Monday the 11th on everything. Yes. That's one of the things we're going to talk about. Don't jump ahead. Don't jump ahead. I got a really good video that shows like how far we've been in the ocean and stuff like that. All right. So I'm titling this Ocean Composition. So the makeup of ocean water, basically. The ocean is the largest reservoir of water, not fresh water, but the largest reservoir of water in general on Earth. And there's that question. Why is the ocean salty? Where'd it come from? And this has to do with several different factors. Salt did not appear in the ocean. It came from the dissolving and the adding of different materials. So whenever you have those things eroded and moved into the ocean, that's when you have the chemical makeup of the ocean change, so there's a higher salinity. So, in ocean water, we have dissolved chemicals that are eroded, or they come from the Earth's surface, so they're washed into the ocean, or they can be blown into the sea by wind, because anybody that's been to the beach knows how windy it can be. There's also material that comes from volcanoes that are underwater. Most of Earth's volcanoes are underwater. That's where we get our new crust from for the Earth, because the crust is constantly recycling. So when we get new crust, that's underwater, from these underwater volcanoes. So the stuff that comes out from the volcanoes is mixing in with the water and dissolving into the water. So that's adding to the salinity. And anything that's been deposited on the ocean floor will be eventually dissolved into the ocean water. So all that combined makes up the chemical makeup of ocean water. And that's why there's salt in the ocean water. It's been dissolved in from different materials. And you may remember us talking earlier about how salty the average ocean is. This is average because most, they'll take all the oceans into consideration and get the average. So you'll have certain oceans that are saltier or have higher salinity than others. And then you have some that are really low salinity. The average is 35 parts per thousand. That's what EPT is. Alrighty, so 35 parts per thousand. That means for every 1,000 grams of water, there is 35 grams of salt. This is 1,000 grams of water, or 1 kilogram. So for every this much water, you have this much salt. So imagine pouring that salt in this water and trying to take a drink. It's going to taste nasty. That would not be potable water. Now we talked about how salinity can be different depending on where you're at, depending on which ocean you're at, and even depending on what part of what ocean you're at. Certain things affect the salinity of the water. Your salinity or your salt content increases if you have a lot of evaporation. We talked about that's the way we separate salt from water. You let the water evaporate, you're left with the salt. So if you have a lot of evaporation going on in the ocean, then you have a very much higher salt content. The freezing of sea ice, again, if all your water is frozen, it's not that easy to freeze salt water. That's why they throw salt down on the ground when it ices or snows. So the stuff that freezes is mostly the fresh water out of the ocean. So you're left with more salt in the rest of the water. The closer you get to coastlines, so the closer you get to the beaches from the ocean open, the higher the salt content usually is. Polar seas, so the extremely northern and southern seas, tend to have a higher salinity. The mouths of rivers should not be under there. Ignore the mouths of rivers for now. I don't know why I wrote that. My bad. The mouths of rivers is where salinity actually decreases, because remember the mouth of the river is where the river empties in the ocean, so you got a lot of fresh water entering in the ocean. That's going to make the salt less. So salinity decreases, or salt goes down, if you're at the end of a river where it empties into the ocean. You got a lot of fresh water coming in. If you have a ton of rain, you're increasing the amount of fresh water into that body of salt water. Or if you have a lot of ice melting, you're adding a lot of fresh water to the ocean. That's going to make your salt content go down. So that's basically everything you need to know about salinity and ocean water. And next we're going to be talking about other stuff in the ocean, most importantly what gases are being dissolved in the ocean, because there's really important things going on with that. You're hot? I'm hot. But I want to wait until y'all say you're hot before I do anything about it. Y'all know that the weather in the school is different from the weather outside, so if they say it's going to be freezing, well, it's going to be 19 degrees, you know it's going to be blazing in here. When it gets closer to summertime, we'll all be wearing sweaters in here. All right, if you can keep going on the same page, that's cool. If not, if you write like I do, go to the next page. All right. Other than things like salt, minerals, and other solid substances being dissolved into ocean water, the ocean also contains a lot of dissolved gases, and we talked about that, especially when it comes to dissolved oxygen. But there are other gases in the ocean that we really need to focus on as well. The three main ones are nitrogen, oxygen, and carbon dioxide. Nitrogen we'll talk a little bit more later. But for now, we're going to be focusing mostly on carbon dioxide. And how these gases get in the water. We know that gases get in the water through diffusion, because we learned that in our freshwater unit. But with ocean, we also get the added benefit of wind mixing the water at the surface. It gets those gases into the water better. And also waves mixing in the water. So waves mix the gas with the water. We don't always have that on fresh water. Some moving water may be able to mix gases in better, but usually your standing water, like your lakes and your ponds, they don't have a lot of movement, natural movement like oceans do. And just like freshwater, there are things that affect how much of these gases are in the water. One is temperature. We learned that temperature affects the amount of dissolved oxygen in fresh water. Same thing with ocean water. The colder the water is, the more gases it's holding. So warm water holds less of the diffused carbon dioxide, the diffused oxygen and nitrogen. So colder water is more rich in dissolved gases. Water that has a lower salinity also tends to hold gases better. So the less salt content in the water, the more gases there usually are. And then with oceans, we need to talk about the pressure. We're going to be talking more about that when we talk the different zones of the ocean. deeper the water is, the more gases are held in because the pressure helps hold it. There are plenty of areas in the ocean that have not been explored yet. I think humans have only really laid eyes upon, what is it, 5% of the ocean? Something like that? Very, very low amount. And one of the reasons is that we can't go very deep because of pressure. Even in vehicles like submarines. Submarines can only go so deep before they implode and everybody dies. We can send unmanned vehicles that can do a limited amount of exploration and gather data for us. You see all those cool deep sea creatures like the anglerfish that's really ugly, but I find really cool. I mean, it's a fish that fishes. It's got a lure. I'm like, that's what you call ironic. Yeah, it's like a little light bulb, little bioluminescent light. All right, last bit we're going to talk about today is carbon dioxide. We talked about dissolved oxygen and how that's important to a lot of aquatic life. If you have low dissolved oxygen, there are a lot of things that cannot live in the water. Same is true for the ocean. You still need dissolved oxygen, still very important. But the ocean is a hub of gas recycling. Gases come in, gases come out, and it helps the entire Earth. So we've got a lot of aquatic plants in the ocean. Sometimes it's lower down on the seabed where there's seaweed and coral and all that good stuff. Sometimes it's more on the surface where there's phytoplankton, little microscopic plant organisms that do photosynthesis. So when carbon dioxide enters the ocean, either through respiration or through diffusion, it combines with the water and there's a chemical reaction. And we know when we have chemical reactions, we have new substances form, yes? Absolutely. Some of the new substances it forms is carbonic acid, which eventually will turn into bicarbonates. And what that is the stuff that shells are made out of. So when organisms form shells around their bodies, bicarbonates is one of the main ingredients. Whatever's not made into shells settles down on the seabed or the ocean floor, and it keeps that carbon material there for years and years. Is anybody still up here? Okay. I'll get to the very bottom. This is it. One of the most important things about the ocean is that it helps take out all the carbon that we have floating around the air. That carbon dioxide that is bad for our atmosphere in large amounts. If it wasn't for the ocean, it would be even worse. The ocean helps take carbon dioxide out of the air. It diffuses it into the water where plants can use it for photosynthesis. And then the plants release oxygen back into the atmosphere. So it helps keep our atmosphere clean. Helps keep a balance. We're going to be talking later about how oceans help affect climates. I know in my class in the 6th grade, we talked a little bit about it because we talked about environments and biomes. How some environments are different because they're near the ocean, because the weather is different. We're going to talk a little bit about ocean currents. We're going to talk a little bit about weather phenomenon like El Nino, what it is, and why it occurs. And then my favorite part, we're going to talk about the different zones of the oceans and what lives in those zones. What sea creatures we have, what's an estuary. And North Carolina tests love to talk about estuaries because we have a lot of them. There's a lot of estuaries on our coastline. Once you're done copying this, this is the end of the notes today. In just a minute, I'm going to talk about what our next project would be. I know that some of y'all in your quarter 2 survey mentioned that you wanted to do more projects. A lot of people prefer to do projects. They love to build stuff, create stuff. That's how they learn. You have different learning styles. And I want to do a project each quarter, but we didn't do one last quarter because of weather and life. My next one, you guys will have about 6 different options about what you want to do. So it'll be like a mini, you get to choose. I'm really excited about some of the choices. All right, real quick, I want to show a short video, ocean introduction. All right, please stay quiet.
From afar, the world is blue, with an all-encompassing ocean, the source of all life. Without the ocean, Earth would be as bleak, as barren, as Mars or the Moon. With every drop of water we drink, every breath we take, connected things that no matter where on Earth we live. Life in the sea generates about 70% of the oxygen in the atmosphere. It absorbs much of the carbon dioxide. The ocean thrives climate and weather, regulates and stabilizes temperature, shapes Earth's chemistry. Water evaporates from the surface of the sea, forms clouds, return water to land and sea as rain, sleet, and snow. The ocean covers nearly 3/4 of the Earth's surface, but that's just the surface. The average depth is 4 kilometers. The maximum 11 kilometers, 7 miles down. Ninety-seven percent of Earth's water is ocean. It should be no surprise that 97% of Earth's living space is ocean space. The greatest abundance and diversity of life is there, with forms that represent nearly all of the major categories of plants, animals, and microbes that exist on Earth. Life abounds even at the greatest depth, where the pressure is more than 1,000 times greater than at the surface. Diving into the sea is like diving into the history of life on Earth, where creatures precede humankind by hundreds of millions of years. It's a vast liquid realm where diaphanous creatures thrive. Jellies, squids, silvery fish. Creatures that illuminate the deep sea darkness with their own livid light. The terrain below holds most of the world's mountains. Entire chains of peaks that run down the major ocean basins like giant backbones. Most of the planet's volcanoes are in the sea, many forming the underpinnings of islands such as Hawaii, the Galapagos, Iceland, and thousands of others. With new technologies, submarines, ships, satellites, we've discovered more about the ocean in the past half-century than during all preceding history. Yet, most of the ocean, about 95%, has yet to be seen by human eyes, let alone explored. Far into the 20th century, people thought that the sea was infinite in its capacity to yield whatever we wanted to take from it, except whatever we disposed of there. Over the years, hundreds of millions of tons of ocean wildlife have been extracted, and hundreds of millions of tons of noxious waste have been put into the sea. Industrial fishing has depleted fish and other ocean wildlife, some nearly to extinction. Many large and even small species of creatures have declined by more than 90% in half a century. Trawls and nets scrape the seafloor to catch shrimp and bottom-dwelling fish, scallops, and oysters. They're the equivalent of using bulldozers to catch songbirds and squirrels. Pollutants from agriculture, industrial waste, and sewage have seeped into the ocean, accumulating in marine organisms, even in the icy waters of the Arctic and the Antarctic. More than 300 dead zones now darken coastal areas worldwide. Plastic debris is dumped in such quantities that a huge floating mass of garbage, twice the size of Texas, is formed in the Pacific. Plastic clogs the shores of even remote Pacific islands. The construction of coastal cities has brought about the loss of coral reefs, mangrove forests, and vast wetlands, and the birds and marine life that once thrived there. Recent changes in the ocean are compounding the impacts of global warming. And in turn, climate change, increasing sea level, and acidification are altering the nature of the ocean. Now we know One of the great discoveries of our time is that there are limits to what we can take out and what we can put in without dire consequences to the nature of the ocean, thus to the underpinnings of what makes life possible for us. Now that we know, we can do what it takes to reverse the troubling trends, to treat the ocean as if our lives depend on it. Because they do.